Okay, this is the first recorded lecture for Math 1101. This is for Tuesday, September 1st. We're getting into Chapter 4, and I expect we'll be doing some Excel here in the near future. We have 3 videos already prepared, short videos, that we'll make available. But Chapter 4 is about personal finance. It's got to do with mortgages and other things. Let's see what this has to do. We're going to get through partway through 4.1. We have the luxury of time, so I don't have to go very fast at all. But what we'll be seeing in Chapter 4 is things like saving money, the power of compounding, and that's why we talked about the exponential curve, because it was so important to see how the longer you let it stay in, the more interest on interest accumulates, and it just gets better and better and better. However, borrowing works the other way around, but how much car can you afford? If you have a fixed idea of what you could afford over a certain number of years, including all the interest, then you could really see how well it could go. What car payment would get you X number of car. We also will talk about saving for the long term, build that nest egg, prepare for the future, whether you call it a nest egg or not. Prepare for the future. Always a good idea to not be shocked by what happens in the future. Credit cards. Seems like everybody's got a credit card. Paying off consumer debt. The best is to not let credit card interest fester for very long, because it's notorious for being the worst of all of them. It's very easy and convenient. Pay off as much as you can per month, and obviously the high interest rates cards will go the first. If you have more than one card, pay the highest ones first, or try not to use them at all. And I don't think we're going to have time to do inflation, taxes, and stocks. If we have time, we might do a quick overview, but I don't believe that's a requirement for the class. I might do it just as general interest for a few moments here and there, because we don't have to always be under the gun to learn everything for a grade. Let's go to the next slide, and here we are into section 4.1. We want to get partway through 4.1 today, and so we'll talk about saving money, the power of compounding. And so we start off with the initial balance of an account is called the principal. It has nothing to do with the principal of a school. It is just the principal. It's a time-honored money type notation. And we'll talk about at first the simple interest. It hardly ever happens except maybe between siblings, or just informally you borrow some money from your brother or something like that. But it's very simple to calculate, but it's hardly ever really used. Anyway, it's calculated by the interest rate to the principal only, not to interest earned. So basically, it's just the same. I think we referred to this briefly in the live class. So the simple interest earned, this is an earned account. You start with the principal, and then you go to the yearly interest rate, and you have the time, typically in years. Sometimes it's in a different framework. And let's see if my pen will work. Yes, it does. You've got principal rate times time. P or I equals PRT is certainly the way that I've learned it in many classes. So I'll put that down. I'm not sure if we're going to need that, but that can be a quick way of saying the same thing. So let's move over to the next slide. Saving money and the power of compounding. And we invest $2,000 in an account that pays simple interest of 4% per year. Find the interest earned after 5 years. Now notice, months has nothing to do with this at all. It has to do with years. And I have to keep hitting that button to get it to work. This pen is going to be kind of tricky to use. So what the point is, 4% is written as a decimal of course, 0.04. The leading zero is up to you. I typically skip it, but as long as you can see the decimal point in front of the 04, that's the main thing. So we put in the $2,000 right there for the principal, and we have 0.04 per year, same as 4%, and the 5 years, the years of course will cancel out. So we'll have the $2,000 for the principal, 4%, 0.04 times the 5 years. Use your calculator, but I could also say that 0.04 times 5 is 0.20, 20%, which happens to be equal to 400. I can tell that that's correct, because 10% would be 200 and 20 would be double that, but that's just something I like to spot check my work, so I'm not off by a tremendous amount. $400, but that's just simple interest. Imagine what you might have earned if it had been compound. It would have been better. Okay, so then we also have compound interest, and that's by far the most prevalent. And it's paid on the principal and on the interest that the account has already earned. So this is where the exponential pattern kicks in. The other was the straight line. This is now exponential. That may be kind of a stair step. It's if you want to get technical about it, it'd be more of a stair step situation versus a smooth curve, at least in a case like this. But that's not, let's not get that picky about it. It's still exponential. Okay, so interest on the interest. That's the way they used to advertise this stuff, and yeah, that's a good way to put it, because before you weren't getting any interest on the interest, you were just getting plain old interest, but interest on the interest is a nice thing. So we have $1,000 invested in an account earning 10% interest compounded annually. So just annually. It's not a great deal, but it's certainly simple to do. So after 1 year, just like simple interest, it's the same as simple interest, because all we're going to do is take 10% of the $1,000 and get $100 in interest. This is a very good interest rate. Let's not worry about the high interest rate. This is just as simple a calculation as they can get, just about. So they earn $100, and guess what? The $100 gets put into the $1,100, to the $1,000. So we have $1,100. They didn't specify that completely, but of course the $1,000 plus the $100 equals $1,100. So that would be in the account after 1 year. But then we go to the second year, and it gets a little bit more complex, because we're going to take 10% of the $1,100. Notice the interest has gone up to $110. That's $10 more than it was a year before, interest on interest. And you add those together, $1,100 plus 110, and that is $1,210. That's an easy addition to do. And so the balance isn't just $1,200, as it might have been with simple interest. It's $1,210, because this is compound interest. Even though it is only annually, typically there's faster ways to do it than that. And yes, they do point out that it would have been only $1,200 for simple interest, because we would have just had the 100 and the 100. In fact, it would be exactly 100. We'll compare the two here side by side. And if you can see this on your screen, I need to maximize the screen. I'm not quite sure how to do that. It's been a few months since I've done this. But for simple interest, the simple one, it's $100 of interest every single time. We leave the $1,000 in the account, and so all we have to do is put in $100 for at the end of the first year. There's $1,100. They already mentioned that. At the end of the second year, $1,200. They already mentioned that. And let's see if I can get the pen to turn on. It keeps shutting off. The battery's running low. At the end of the third year, another 100 makes 1,300. Now they've decided to skip ahead a few years. At the end of 10 years, it works out to be 10 times 100, another $1,000. In addition to the original 1,000, you're up to 2,000. At the end of 50 years, you've earned all that interest, simple interest for 50 years, $6,000. That sounds like a lot of money, but don't let them sell you on that. I don't think anybody's going to try, but compared to the bottom line down here, a slight difference there of $117,000 versus $6,000. Yeah, there's quite a difference. Of course, this assumes you've got 50 years on the clock to let this happen. Not everybody will do that, but anyway, let's take a look at what we just learned from before in table form. And the growth, of course, was very constant before, but now it's inching up. We already saw the first year was just the same, the 100, but now we're up to 110 the second year, as we already explained. But then we take a look at the third year, and 10% of the $1,210, which is in the balance, is now $121. You add that together, and here's our growth of 121, but the balance is 1,331, which is fantastic. They somehow didn't have room for the end of year 1, end of year 2, end of year 3. It's the same as this. They just didn't print it out. And then they skip ahead and go to year 10 and year 50. And we can see how at the end of year 10, although my handwriting isn't the best here, $235.79 is the interest. And they'll round to the nearest penny. Every time it's round to the nearest penny, so don't be concerned about that. The balance is up to $2,593 and change. But then, by the time you get to year 50, as you conclude year 50, the interest is $10,000. And that's really spiraling. And it's really getting to be a pretty sweet deal. $117,000, as you can see, a major difference between the two styles. So compound interest is interest paid on both the principal and on the interest that the account has earned. Okay, the compound interest formula is a little bit more complicated, so we have two different versions. And the balance after T periods will be the principal that we've already mentioned, But then we have this 1 plus r to the t power. So this is something we have to explore a little bit. In fact, we have two different ways of writing it. And I typically show both, but this is the complicated one, this is the easy one. And I typically go to the easy one. But let's take a look at what's involved here. What is r anyway? We have the APR, the annual percentage rate, which is divided by n times per year. Very frequently that ends at 12 for months, especially for mortgage payments and credit card payments. But now we're earning money, and we're not going to go to E, which is continuous compounding. That's beyond the scope of this class, as it turns out. But it could be paid daily or once a year. We've just been doing once a year recently. But Y is the number of years. It looks like NY or New York or something like that. So R has been replaced by APR over N. I'll just draw an arrow. And the time, T is time, I didn't say that, but T is time, will be replaced by NY. Number of times per year, which might be once a year, that makes it easier, and then Y is the number of years, so we'll just have to see how that's going. For now, it looks like we just have once per year, and then anywhere between 1 year and 50 years, so that's the idea is. So most of the time, we kind of will find that we're reverting to this one, because this will become kind of common knowledge. We'll be seeing this over and over again. And same with this. We'll be seeing both of those frequently enough that they'll be kind of understood, believe it or not. Let's take a look at the breakout of the formula. This number of periods was just n. So as I restart my pen, it doesn't seem to want to stay on. Battery is slipping. Yeah, just about lost the battery on it. So APR over n. They're just finally explaining it a little bit more fully. Multiply the period interest rate by the number of periods in a year. So we have to find the period interest rate. Now, if it's once per year, that's going to be the yearly interest rate because we're dividing by 1. Nothing's going to happen. But if it's monthly, then you might take, say, 12%, divide by 12, and find 1% per month. Let's just take a look at an example. What if we had 12%? But we're going monthly, so I'll put in the word monthly. And that would be 1%, 12 over 12 is 1, that would be per month. Now the per month would be understood, but it doesn't hurt to say it, and that would be your period interest rate, the APR formula, and so that could also be known as R. So they haven't called it R, but I'll go ahead and put the R down. So R would equal 1%, or you could even say 0.01 is equal to R. So for computation purposes for Excel or your calculator, we'll take a look at both, but we'll try to depend on Excel quite a lot if we can. 0.01 would be the useful number, but 1% is also true. So here's an example. Suppose we invest $10,000 in a 5-year certificate of deposit, a CD, that pays an APR of 6%. So that's annual percentage rate, annual. What's the value of the mature CD if the interest is compounded annually? So I'm going to start off with what N would be. N, the number of pay periods per year, as I restart this pen, would equal 1. Quarterly is 4 times per year, like once a season. 4 times. Monthly, that's a very common one. Call it 12. Daily, although we know we have leap years. I've even seen 360 used, but right now they're going to use 365. That's probably the worst calculation because it gets to be pretty hairy, but we'll talk about that another time. But we'll see a little bit of the daily stuff too. So let's skip ahead to the next slide and take a look at some of these, and I'll see about looking at the first one, which should be the easy one, the value of the mature CD when it's done annually. 6% is 0.06, and R, APR over 1 is 6, so we didn't have to do much. I wish this pen would stay on, but anyway, 0.06. Anyway, I can't seem to write it, but you can see that it would be 6.06. T is 5, so this is a simple calculation. R didn't change, so that's what makes it easier. And we have 10,000, and I would just say 1.06, which they finally did down here, 1.06 to the 5th power. And so find this part first. And my highlighter pen isn't really working well, but anyway, go ahead and do that part first, PEMDAS, and then multiply by 10,000, or slide the decimal over 4 spots if you prefer. And we see that after 5 years, a pretty handsome number, 13,000 and change, not too bad. Now, how does this compare to quarterly? Now, before they didn't show the division by 1. I guess they figured it was obvious, but if we have division by 4, that means per quarter, per 3-month period, we would have 0.015. That's also known as 1.5%, but let's keep it in decimal form. I know it's traditional to talk about percentages, but calculators in Excel really do like decimals, so let's try to do that. But now notice the same time that this is diminished by a factor of 4, this is increased by a factor of 4. So we're kind of pulling in opposite directions, and they don't exactly cancel out. It turns out the more times you get paid, the better off you are. And the book will explain more about this. But you've got 20 pay periods. So 20 periods, 20 quarters is what you have over 5 years. So 5 years times the 4 quarters. So that means you get a 20 out here in your exponent. So this would be 1.015 to the 20th power, and yes, of course, the 10,000 goes last, even though it looks like it goes first. So this is a little bit more as I zoom back. That's 13,468, 13,382. Looks like it's gone up about $80, $86 or so. Let's just compare the others, and maybe we'll call it a night after that. Monthly, a very common one. I'm glad they picked 6% because this goes in evenly. And this is also like saying, as we divided by 12, the 6%, that was annual, A for annual, and we get 6% divided by 12. This is 0.5% per month, but that doesn't matter. Leave it as 0.005. The leading zero is up to you. But instead of the 0.5% looking kind of small, you get paid 60 times. So that part's getting better. And so the number is inching up. The 10,000 principal is the same. 1.005 is the 1 plus R, which I would just write that way. You don't have to include this step if you don't want to. And then put in the 60. Background steps help. That never hurts to show your work. I think it's fantastic when you do. And we can see how the money's comparing. It was 13,468, 13,488. It's gone up by another $20. Well, it's slowing down a little, but it's still increasing. What about daily? Do we get paid tons and tons of money for daily? One might guess that's the case, but let's take a look at dividing the APR by 365. Now this will involve round off error, so this is where very often you have to keep many more decimals than they are doing right here. So that's a little bit frustrating when they've not decided to follow the rules. But anyway, let's just go with it for now. And simple example, we're not going to worry about the details yet. But now they're getting paid very small, 0.00016. That is also known as 0.016 of a percent, and that is rounded, unfortunately. But the good news is they get paid a lot, over 1,800 times. So they've already put it with the 1 already, 1.00016. But look at that huge power. The round-off error could be really bad. Occasionally it's not, but it could be really bad. And I have not double-checked this, but it's gone up not that much. The main point I'm trying to make here, from 488.50, 13,488.50, 13,498. It's only gone up about $10, not even $10. Now that's frustrating. The big jump was between annual and monthly. That was a big jump. Or annual and quarterly, I should say. So right in the beginning, it jumped a lot, and then it slowed down. So it's not what you might have expected. I might have expected that 4 wouldn't make that much difference, but 1,800 would. But no, the R got chopped down by quite a lot to make up for that. So that's a tad frustrating because that number is so small. Even though this number is big, it's still going up. That is still increasing. That's important to notice, but it's not increasing as fast. So I don't want to confuse anybody. Still a better deal. In fact, the best deal is when you get paid continuously, but then you have to bring in E and logs and stuff like that, that's for a different class. College algebra would handle that kind of thing. We will actually see logs briefly here, but only briefly in a certain context, so you'll not have to worry much about logs and not at all about E. The E will not be part of this class, so in case you didn't care for E, that's the way that goes. Let's kind of summarize these, and they increase, and certainly better than the 10,000. So that was the yearly total, and that was the quarterly total, monthly total, and the daily total. So we had a $86 increase, followed by about a $20 increase, followed by about a $10 increase. So that is curious, so I'll go ahead and put that down. These are just rounded to the nearest dollar. I'm not worried about the cents right at the moment. That was a $20 increase, and here's the plus $10 increase. But the point is they're all increasing, and that's a good thing. So I think I'm going to stop here. There's another formula, but I will save that for the next lecture, and that will be live on Thursday for all of you. Thursday lecture. We'll start with the middle of 4.1. We'll start to sprinkle Excel in as it becomes relevant. And anyway, stay tuned, and we'll talk to you live on Thursday. Have a nice day.